Hello everyone. So today we are going to discuss the bi-weekly contest question, the question number 4th, which is Leetcode 3426, Manhattan distances of all arrangements of pieces. So what does the question say? You're given three integers m, n, and k. Okay. And there's a rectangular grid of size m by n containing k identical pieces. Return the sum of Manhattan distance between every pair of pieces over all the valid arrangements of the pieces. Okay, so what do we have to return? We have to return the sum of Manhattan distances between every pair of pieces over all the arrangements of pieces. And a valid arrangement is a placement of all the k pieces on the grid with at most one piece per cell. So it means every cell contains either 0 piece or 1 piece, isn't it? Since the answer may be very large, return it modulo 10 power 9 plus 7. Okay, so we have to return the answer like this, where mod is 10 power 9 plus 7. So the Manhattan distance between two cells, this is the definition of Manhattan distance. And I assume we already know that. So if we are given two coordinates, x1, y1, and the second one is x2, y2, the Manhattan distance is given by x1 minus x2 plus y1 minus y2, isn't it? Now let's take a look at this example. So in this example, we're given a 2 by 2 grid. Okay, so it's a 2 by 2 grid. Fine. So we have only 4 cells in here. So the output over here is 8. So they have drawn all the possibilities for us over here. Okay, so the number of pieces is 2. So we can place the pieces like this, like this, like this, like this, like this, and like this. And you can think of it, there is no other possibility of putting all the pieces. Now let's find out the sum of all the Manhattan distances between all the valid arrangements. So these are all the valid arrangements. Okay, these are all the valid arrangements. All the valid arrangements are drawn in front of us. What is the Manhattan distance over here? The Manhattan distance between the two pieces is 1, right? Over here it's 1 again. Over here it's again 1. Over here it's 1, isn't it? Now over here the Manhattan distance is 1, 2. So it's 2. In this case it's again 2, 1, 2. If we add these up, we get 8. So how do we approach this problem? Now, because if the grid is bigger, it becomes really complex to visualize all the possibilities. Even if we see the constraints, the value of k can go up until 10 power 5, right? Because m by n, m multiplied with n can go up to 10 power 5. So how do we approach this? Let's think of the intuition to approach this problem. So over here, I have drawn a grid. I have not drawn all the lines because the already made lines will do the work. I hope you can see them. So what is the dimension of this grid? So if we see, there's 1, 2, 3, 4, 5, 6. There are 6 rows, right? So the value of m is 6. Okay. And over here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the value of n is 9. Okay. So this is a 6 by 9 grid, isn't it? Let's say we have some value k. So there will be k pieces put inside of these grids. Now those k pieces could be arranged like anywhere, right? Suppose a piece is here, 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 like this, isn't it? Like there are multiple ways. So let's discuss how many ways will be there to put these k pieces into the grid. Well, that's simple. We just have to select k cells. Okay, we just have to select k cells out of n times m cells, right? So that would be simple. That is simply this, n times m c k. Simple combinatorics, right? Okay, but we don't need that, right? We don't need the number of ways to select k cells. Okay, but this information, let's see what we can do with it. So we have to find out sum of all the Manhattan distances, right? So let's just first of all focus on picking up only 2 points. Okay, picking up only 2 cells in here. Let's say we pick this cell, and let's say we pick some other cell like this cell. Okay, if we pick these 2 cells, how many other cells that we are left with? Left with k minus 2 cells. Now we can arrange those k minus 2 cells in the remaining space as we want. We can arrange those k minus 2 cells, the remaining k minus 2 cells, in the remaining spaces as we want. So how many spaces do we have? We have a total of n by m space. We have to subtract 2 because now these two spaces are acquired by our red and yellow pieces. So how many ways do we have? We have actually n multiplied with m minus 2 c k minus 2, right? And what is the distance between these two cells? The Manhattan distance, it's 1, 2, 3, 4, 5. So obviously we have to add this to our answer. 5 multiplied with the total number of arrangements, right? Total number of arrangements. Just for these two cells, this amount of number will get added, right? Just for this pair of cells. Now think of how many pairs will be there. We basically have to choose cells like this, right? We basically have to choose cells like this. And we have to find out the Manhattan distance of those cells. So for this case, for this just one case, it's 5, right? But think of all the ways of choosing two cells on this grid, okay, and finding out their Manhattan distances. So I will repeat myself again. What we have to focus on now? Sum of Manhattan distance by placing two pieces in all valid arrangements. So I'll represent this value with d. So if we are able to find it out, the sum of the Manhattan distances that we get by placing two pieces in all valid arrangements. Okay, so we placed two pieces like this. Now we could place two pieces like there are many ways to place the two pieces. Like I can only shift this red one over here. This is a new valid arrangement. Now we find the sum again. Now I can place it over here. We can find the sum again. Place it over here, find sum again. Place it over here, find sum again. Now I can place it over here and find sum again. So like we have to add up all these sums. Okay, we have to add up all these sums and find it and store it in a value d. That is our target. Okay, and since every one of these pairs are repeated this many times, we will simply multiply that answer with this. Okay, so our final answer is going to be d multiplied with this. Okay, so this is our goal. So we have kind of simplified our problem. Now we have to be focused on finding out the d, right? So I can represent this d as x1 minus x2 plus y1 minus y2, isn't it? And we have to find out the sum of all the possible pairs. Yeah, to find out the sum of all the possible pairs on the grid. But listen, important thing about the Manhattan distance is that we can separate the x and y's. Like even if you see this mathematically, yeah, this summation and this summation is independent, isn't it? I can do this, right? This is the value of d now. Okay, but how does it help? Let's now just focus on calculating this first of all, right? x1 minus x2. So like it's the two different rows. So I said we should just focus on computing this one, right? So let's try and focus on computing sum of all the Manhattan distances of the possible x values, right? On the grid. All the x values now we have to be focused on. So let's take this column for now, okay? Okay, so all these x values are different, right? This is different, right? All these x values are different, right? I'm just focusing on one column for now. Let's say we take a pair. So let's keep this fixed for now. Now, if we select this cell and put our piece, the Manhattan distance would be 1, right? If we select this cell and put our piece, the Manhattan distance would be 2. If we select this cell and put our piece, the Manhattan distance would be 3, right? And so on, right? It would be 4 over here and then it would be 5, right? If we keep this cell fixed, right? Now, let's fix some other cell. Let's say we fix this cell now, right? Now, since we have already taken Manhattan distance between this and this, we won't be taking the upper cell now. Again, the Manhattan distance between this cell and this cell is 1. Now the Manhattan distance between this cell and this cell is 2. and then it's 3, and then it's 4, right? Okay, now let's change our cell. Let's take this cell now. Again, we have taken the upper cells. So now it's 1, 2, and 3. You see the pattern? So it will be 1, 2, and 3. Yeah. And then for the other cells, it will be 1 and 2. For the second last cell, it will be just 1. Right? So this is the total sum of Manhattan distances for only selecting the cells in the very first column. Let's just try and compute this. So if you look at the pattern over here, how many ones are there? There are 1, 2, 3, 4, 5, right? And how many cells were there? 1, 2, 3, 4, 5, 6. So the value of m was 6. So can I say that it is like saying 1 multiplied with m minus 1, right? And then it will be 2 multiplied with m minus 2, because there are 4 2's, right? And the value of m is 6. And then it's 3 multiplied with m minus 3, 4 multiplied with m minus 4, and then it's 5 multiplied with m minus 5, right? And for m number of cells, this process goes on, and it will be finally m multiplied with m minus m, which is 0, right? Okay, so we kind of see a pattern over here. Now if I want to generalize this mathematically, I can write it as summation x multiplied with m minus x. The value of x goes from 1 to m. This is how I would like to simplify it, right? But this is true if we are selecting the 2 points, if we are selecting the 2 cells only from the very first column. But we don't have only one column, right? We have so many columns. Like we have this column, we have this column, we have got this column. Note that this is true when we are assuming that there is one cell in every row. We assume that there is only one cell here. We assume that there is only one cell here, right? Only one cell in every row, we assumed. But actually, how many cells are there in every row? In every row, there is n cells, remember? N cells, yeah, because it is an m by n grid. So every row has n cells, isn't it? So since we have to choose 2, right? We have to choose 2 cells, right? So here we have how many choices? In every row, we have n choices, isn't it? In every row, we have n choices, not one choice, but n choice. We focused on finding that value based on one choice, but every row we have n choice. We have got n choice here, we've got n choice here, isn't it? We can select this and we can select this, right? We will still be getting 1, 2, 3, right? But we are getting 3 for this, we're getting 3 for this, we're getting 3 for this, we're getting 3 for every one of them, right? So what we need to focus on, that there are n ways of selecting a cell from here, and there are n ways of selecting a cell from here, right? So how many ways are there in total? In total, there would be n squared ways, n times n. So this value, this is true if we are assuming one cell in every row, okay? But every row has n cells, which leaves us with n squared choices. So it is n squared multiplied with this. Okay. So that is the value of x1 minus x2. All the possible summations. Let's simplify it. So it will be n squared, that's summation. I can write xm minus x squared, right? And the value of x goes from 1 to m, isn't it? So it's now n squared. I can separate the two, xm minus x squared, and the value of x goes from 1 to m, x goes from 1 to m. Now n squared multiplied with, since m is a constant, I can take it outside. Summation of x goes from 1 to m, minus the summation of x squared, x goes from 1 to m. Now we are here, We are familiar with these formulas. What is this summation? It is like summation from 1 to m. We already know it is m into m plus 1 over 2. So this now becomes m into m plus 1 over 2, right? And what is the summation of 1 till m? Every term is squared. We also know that it is equals to m times m plus 1 multiplied with 2m plus 1 over 6, right? And don't forget the n squared on the outside. We can take m into m plus 1 as our common. So n squared multiplied with m into m plus 1. We are left with m over 2 minus 2m plus 1 over 6. If we simplify, we get 3m 2m minus 1. Now we're left with n squared m plus 1. 3m minus 2m is m minus 1 over 6. Well, m plus 1 multiplied with m minus 1, we can simplify that too. It's simply m squared minus 1 over 6. So here we are. All the possible summation of x1 minus x2 is equals to this. Derived a formula for this, right? Similarly, we can derive a formula for this. Well, it will be m squared n. We just have to replace the m with the n's, right? N squared minus 1 over 6. So the value of d we already found out, right? This is the value of d now. The value of d what? The value of d was summation x1 minus x2 plus summation y1 minus y2. So the value of d is actually this plus this. We found out the sum of all the Manhattan distances that we get by placing two pieces in a grid of n by m. That will be the sum of all the Manhattan distances. And we just have to multiply this d with all the possible arrangements of the remaining k minus 2 pieces. All the possible arrangements of the remaining k minus 2 pieces. This is our answer. We know the value of d. We know the value of the combinatorics. Now, finding this thing in code could be a little bit trickier because what is this? What is the formula for the combinatorics? The formula for the combinatorics is n multiplied with m minus k factorial divided by k minus 2 factorial multiplied with n minus m minus k minus k minus 2 factorial, right? And you have to multiply d with it. We already know the value of d, right? So we need to find out this. Now, this is a factorial, right? So we can calculate factorial. And remember, we also have to tell our answer by taking a modulo with 10 power 9 plus 7, right? So we have to write a factorial function, right? To find out this, and this, first of all, right? We have to write. So let's focus on computing this value, this NCR value, right? How do we do that in code? So first of all, we need a factorial function to compute this, and this, right? So how does our factorial function looks? It looks like this. So this is my factorial that I will use to compute this, and this. I'll call this value a. Okay. So let's call this value a. So a would be equals to factorial n multiplied with m minus, oh, here it should be minus 2 because this much of a space is left. Here also it should be minus 2. Yeah. We are having a vector to pre-compute some of the values so that some values are not computed again and again. Okay. And now this is a. Let's say this is b. So b value would be the same thing. just instead of this, we have k minus 2. And what is our c value? Our c value, factorial of this. Okay, this a value is my numerator, right? This is my numerator. And what is my denominator? My denominator is b multiplied with c. Yeah, I can take its modulo as well. So what we need to find is a over b. The problem is because it's a modulo, right? We have to find the answer in modulo. So how do we do that? So for that, we need to compute the inverse modulo. And how do we do that? If MOD is prime, if it's prime, we can use the Fermat's little theorem. So basically, this numerator over denominator, modulo mod, computed as numerator multiplied with denominator powered minus 1 percentage mod. Now, what is this powered minus 1? This is not the normal powered minus 1. This minus 1 signifies inverse modulo. Okay, this minus 1 signifies inverse modulo. And what is inverse modulo? Inverse modulo, this value is actually equals to powered mod minus 2. So we need to have a power function as well that computes the power a powered b, something like that, right? Because to find out the inverse modulo, we need it. Okay, and this is the inverse modulo of den. So this is our power function, okay, to compute x powered p, right? This is how we write it down. I'm not going to explain this because you most probably should know. Okay, so we were here, right? We were here. We computed a, b, and c. So after computing a, b, and c, we need to compute a over bc, right? This is our numerator. This is our denominator. So I'm just going to redefine. Numerator is a and the denominator is b multiplied with c. And never forget to take modulo. So what is our NCR value? Our NCR value is going to be a multiplied with the inverse modulo of den. Okay, the inverse modulo of den. And what is the inverse modulo of den? Well, if you look it up, the inverse modulo of den, I've already told you just right now, is actually den raised to the power of mod minus 2. Okay, so we have to take again the modulo. So what was our d value? The value of d was this. Yeah, so let's copy it over here. Okay, I'm gonna call this as x. I'm gonna call this as y. Okay, I'm gonna call this as x and I'm gonna call this as y. Fine, so this is my x and y. And finally we have to return x plus y multiplied with NCR, all of this divided by 6, right? But it's not that simple. We need to take a modulo on the top, right? And now since again we are dividing, we need to take the inverse modulo, right? So what do we need to return? We need to return x plus y multiplied with NCR value, right? We take its mod and then we multiply it with the inverse modulo of 6. What will be the inverse modulo of 6? It would be 6 raised to the power of mod minus 2, right? And we again take the mod of all of the answer. So we finally return this. So how does our entire code base look like? So this is how our final code looks like. First of all, since these were in normal integers, I converted them into long, m, n, and k, right? Okay, and this is for the factorial. We calculated the numerator, right, which was this, remember? Then we calculated the b and c value, and then we calculated the denominator, right? And now we need to compute the ncr. Ncr was nothing but numerator over denominator, so it's numerator, and this is the inverse modulo of denominator. Okay, so we calculated the ncr value, and then we finally found out the d value. D was what? X plus y upon 6, right? So we first calculated the x value, the y value, yeah, and then we did x plus y multiplied with ncr, and then we divided by 6. So this is again our inverse modulo, and finally we return our answer. Okay, this code works. I'll upload a GitHub link to this code. You can check that out as well. Okay, hope it helps. Hope you understood the proof. This proof was the most important part of this problem. Okay, thank you.